Okay, good morning everybody. Welcome back to Motion Plan. Today we are wrapping up our analysis of sampling-based motion plans. And we have like three major topics that we look at. The first one is that we revisit some of the theories that we had before and tighten it, and also look a little bit more into breadth, different kinds of theory. We will also have in total 5 additional planning algorithms that are just kind of variations of what we have already learned. So we won't go too much into detail, but it will be hopefully quite interesting to see what you can tune in order to achieve different results. And then finally, I also hope that we will look into optimization, just like for 5-10 minutes, so that you're prepared for next week when we actually look into how to use optimization in motion planning settings. Okay, so to recap, what we have learned so far in sampling-based motion planning are different algorithms. So we looked at the geometric case, where the most prominent examples were PRM, or probabilistic roadmap, and RRT. And then we also looked into the kinodynamic case, where the most basic version was kinodynamic RRT. And then on top of that, we considered the case where we might also want to optimize the cost function of, for example, minimum energy or shortest path. And in the geometric case, we learned about RRT star, bit star, and SST, not really the star version, but the plain version. And in the kinodynamic case, we learned about AOX, which was this meta algorithm where X can stand for RRT, for example, and also SST, which can be applied to the kinodynamic case. And then last week, you learned about kind of how to actually do things in practice, which is this Open Motion Planning Library, or OMPL for short, which you will also use in the third programming assignment that we have posted last week. Okay, so with that, I will start looking into more theoretical insights. And for that, we first need a few more definitions, and then we kind of see why they are useful. So the first thing is a robust path or trajectory. And so let's assume we, like for a second, we can assume we are in 2D. We basically say if we then can put like a circle around our solution trajectory, and none of the points in the circle will be on top of an obstacle, then it's kind of robust with respect to the size of the circle. And then in d-dimensional cases, it's not a circle anymore, it's some sort of ball. The distance, the radius of the circle is dependent on our distance metrics that we also used in a different context before. And so as long as there's some sort of finite size of this ball, so the delta is greater than 0, then the solution that we have is known to be robust. Now we can use that property to define robust feasibility, and the motion planning problem we have is robustly feasible if we can find a solution so that's robust. And then you can also extend it for optimality. So if you're interested in a robust optimum, then you would first constrain your solution space to have only robust solutions, and then essentially takes the minimum of all of these solutions, and that would be your robust optimum of your motion planning problem. Okay, so that's very abstract. So maybe let's also look at a picture here. So we have this funny 2D case with obstacles. We have a start configuration and a goal region. And then the optimal solution in this example is this one. So you can see that it it's a bit hard to see. And then if we want a robust solution, then we essentially make sure that there's always some clearance. So that means here the robust solution has to kind of go a little bit further away for it. And then for all of these possible robust solutions, we also want to minimize costs, like the passes again, typically for given delta or epsilon. Okay, so why do you think that definition is useful maybe in the context of we want to do some theory next? Yeah. Okay, that's very good because it's also already taking it into the practical things, what happens if we execute the motion. Typically in motion planning, we don't care. We only care about the plan itself follows like our definition. So can you also think of like a reason why this definition could be useful just for the planning? And you can use that example on the right. So that's kind of one motivating example why it's useful. Yeah. I think that hits the essence. So in this concrete example, the two obstacles touch at one point. So a bit hard to see. But then a sampling-based planner like RRT, in order to compute the solution, it would really need to sample exactly this point where the two obstacles touch in order to find a solution at the end. And the probability of sampling exactly one point is always zero because the point has kind of an area or volume of zero. And so in kind of the following, we will kind of deal with these sort of probabilities. We want to always make sure that the probabilities are strictly greater than zero. Okay, and so we have multiple properties that we looked at. One of them is completeness. And the definition of completeness is that an algorithm is complete if in a finite time it always finds a solution if such a solution exists, or it returns or tells us that a solution does not exist. Do you have any example, ideally, of an algorithm that we have learned in this class that has the property of completeness? No, not quite this definition, but close. Yeah? Yeah, so the classic one is A star, and we come back to RT in a second. Okay. Then we had something like resolution completeness. That's almost the same thing. The difference is that we now have this kind of finite resolution step epsilon that is typically user provided and greater than zero. But otherwise, it has the same two components. So if a solution exists, it's guaranteed to find it in finite time. If it doesn't exist, it is guaranteed to tell us in finite time that it doesn't exist. Can you think of any algorithms that we had in class? Okay, so that's much harder. So we had also in the search-based area, we had the state lattice we saw. We first created these motion primitives that were aligned with these lattices, and our decision on which primitives we selected and how kind of fine-grained the lattice is also kind of decided this epsilon, how resolution complete we are. And then finally, we have probabilistic completeness, and that one means that the probability of finding a solution converges to 1 if the running time goes to infinity. And so in particular, we don't have the second component anymore because it doesn't make sense to say it doesn't exist, because this algorithm would need infinite time to even figure out if it exists or not. So typically we drop that, even so in some cases it might be possible to decide if it doesn't exist. If it's, for example, if the whole goal region is kind of in not in free space but occluded, then we can figure it out, but in general not. So what's an example for probabilistic completeness? Exactly. So this one is RRT. Okay, and of course they're all kind of related, but depending if you're like in discrete space or continuous space, there's a slight different variance. Okay, and so the first thing I want to revisit is the completeness of geometric and also dynamic RRT. A little bit closer to kind of this paper. So always when you look at the theory, you will find these references, and then in the slides you can see the exact details of which reference it is at the end. And so in RT, we have already discussed this completeness result, but very informally in pictures, right? So we looked at this series of Paul's argument and then tried to reason that, yeah, there should be a solution. And so now we want to look at it a little bit more formally, how it was also written down in this pretty old paper, so you get an idea how that is done. And just to recap, like the algorithm, I think most of you know by heart now because we had to implement it, and it makes us memorize, but it has these sort of 3 major steps. That we first sample a point, we find the nearest point that is already in the tree, then we go in that direction, potentially with some step size, then we check for feasibility, and if it's feasible, meaning there's kind of no collision, then we add both the vertex and the edge to our solution graph. And then the proof, like before, assumes that there exists a solution, and that solution is also now robustly feasible. That's why we have this definition, which graphically exactly means we have these kind of spheres that we can put on top of the solution that we assume exists. And then that also means that we have a discrete sequence of these configurations and or actions, depending if you're in a geometric or kinodynamic space. And then formally, the proof is by induction. So the induction proofs always have the same structure. You need a beginning, you need a hypothesis, and then you need the induction step. So the beginning is, also the hypothesis is basically was these different discretized solutions from 0 to k plus 1, and we assume that we found a solution from the start to that particular discretized point. And then for the induction beginning, that is trivially true because I equals 0 means we are at the first configuration. By definition, that is our start configuration. And then in the pseudocode, we always add the start configuration to the tree, and therefore it's in the tree and we are good. So now it's kind of the induction step, which is usually more interesting. Formally, it means now we assume that our assumption holds for I, and we show that the property of our hypothesis is also valid for I plus 1. And then they start and say, now we make an assumption about volumes. In 2D it would be areas, in 3D volumes. In higher dimensions, that's fine, but also still possible. And so we assume that for each of these Voronoi regions, remember every point in our tree defines kind of a Voronoi region, and then this nearest neighbor sampling means that we find the node in the tree that is kind of the Voronoi center of the point we sample. So we assume that this volume is just lower bounded by some constant, so it is strictly greater than 0. And that at the end just means that we never have a density where we have just a single point. So I think this assumption makes sense as long as we have finite points in our space. And then we can play a little bit with probabilities. So the probability for selecting this I point is basically just looking at the ratio of areas. So you look at how large is the Voronoi region of that point I, and how large is the region in total where we can have free space. And then we can bound it because we assumed we had this little bound C1 and say, okay, that is some positive number at the end. That is more or less fixed. So this probability is strictly greater than 0. Then this assumption is a little bit stronger. So we now assume that the probability of finding some sort of action or action sequence for going from this I point to the next point is also non-zero. And in the geometric case, I think it's maybe intuitive that that is possible. In the kinodynamic case, if you remember, I think 2 weeks ago we discussed this small time controllability. We have to have additional assumptions for this to be true, right? So that we have kind of a nice dynamical system where we can always find sequences of actions like that. And then we can also formally bound against the probability. So the probability to connect, or PC, will always be greater than the probability of sampling, like getting from I to I plus 1, times the probability of selecting I in the first place. And that just assumes that those are two independent events. That's why we can multiply the probability. And then we can compute the probability to connect after multiple iterations or attempts. So let's say we sample multiple times, j times. What would the probability be then? And it's basically the probability of not connecting in one step, which is 1 minus PC. Since all of these things are assumed to be independently sampled, if I repeat it j times, I will basically get 1 minus PC multiple times, and they get multiplied, and that's why we get the power up here. And then we're not interested in the probability of it connecting, but two connectings, we again take kind of the inverse event and do 1 minus that. And then the final step is just to take the limit, and that's a nice series because we established that PC is non-zero. So it means we have here a number that's below 1, take it to a power. This term essentially becomes 0 in the limit, and we get the desired result. Okay, any question regarding this slightly more formal proof of the series of balls argument? Good, then I have a question for you. I started this robust feasibility. So why it didn't really appear here? Why was that important? Yeah. Mhm. Yep, perfect. So basically, it's very much hidden in this original proof, but it's related to one of these two assumptions, not holding true if you have a problem that's not robustly feasible. Okay, and then this is a nice induction proof, and we had this like problem before, so let's revisit it also. Why isn't it sufficient to also show asymptotic optimality? Where the argument is, instead of just assuming that this initial sequence is a solution, we assume it's the optimal solution. Mm-hmm. Exactly, and that's kind of the same here. We would somehow need to show who exactly the parent is, and also that right now we only reasoned about connections of these two balls, but we didn't reason about the connection being optimal, right? So we could also have technically a connection that's kind of funny looking every single time. Okay, so that's good. So we have now seen a little bit more formal way of this series of balls argument, and it turns out that not all RRTs are actually complete. And that's a bit harder to grasp because the proof seems to be quite straightforward and nice, and actually coming up with cases where some of the assumptions are not fulfilled is much harder. And there's been this paper, which I forgot how old it is, but it's not that old, and they looked at one particular variant of RRT, where they then showed by counter examples that it's not complete. And I think that argument is quite interesting, so let's look at it in more detail. So the variance they look at is that they don't sample the time step, but they use a fixed time step. And that's actually something that is super common when you implement it, because often you're kind of too lazy to sample the time step. So that's not wrong, I would say, like at least intuitively, I've implemented it like that often. And then the second variant is that they use something they call best input, which is an analytical version of guided Monte Carlo. So that basically only works if you can solve a two-value boundary problem, or if it's a kind of a geometric case. But just kind of informally what it means, let's say I sampled this random node here, then I use my KD tree to find the nearest node, which is this one. So in Monte Carlo, in guided Monte Carlo, what we tried was k times, here 7 times I think. We kind of sample and then pick the one that seems to be best with respect to our distance metric. In the best input case, instead, the idea is that we can immediately compute what is best. And you can imagine in the geometric case, it's quite easy. It's literally just the lines that connect the two going by step size. For some kinodynamic cases, it's also fairly easy because it might be like a small optimization problem that has maybe even an analytical solution. Okay, and then the examples they came up with is very concrete, but also super abstract. So it's a two-dimensional problem, which has kind of the state space x1 and x2. And it's a kinodynamic problem with a single control variable. So your control variable can be between -1 and +1. And then the change of your variables is defined like that. So the change of this x1 variable is simply just u, so linear. And the change of the x2 variable is u squared minus 3. And then if you kind of look at the limits of u, you can calculate that kind of this change of x2 is always negative, right? So it's in kind of the one case, if you select 1 or -1, this basically becomes -2, and if u is 0, then this becomes -3. So it's kind of in this range. And then if you would graph the whole thing, it looks like that. So you start at some fixed point, and then because our time steps are always these fixed delta t's, I don't know what kind of concrete numbers they used here, but then depending on the u, after the first time step, we get this sort of like quadratic parable. And then after 2 time steps, you again have to take each of these potential points and then plot each of these potential actions. So you get more interesting two-dimensional shape. And after 3 times, it's the same, like even more interesting shape. Maybe what's important to note is that you can never go back. So when you start at 0 here, but then in x2 you're maybe at 0, but because your x2 dot is always negative, then at the next time step you're somehow down here, right? And there's no overlap in these different time steps. Not super intuitive robots. You have some sort of take back, right? But in this example, that's okay. And then the counter example is the following. So they assume that they already have a tree with 3 nodes. And they say that basically complete algorithms need to recover from any intermediate tree. And the concrete tree is the following. You have this initial nodes that are obviously always in there. And then you have the 2 extrema points. So basically the states that you would reach if you apply -1 as action, and the states that you would reach if you apply +1 as action. Okay, so you have this tree, and then the argument is that now if you sample any point, there are large regions that you can't reach anymore. And they're marked in this picture in gray. So for example, this gray thing you can never reach, and that also propagates that for this time step like 2 delta, you can only reach these black parts but not the gray parts, and so on here. And why is that? For that we have this funny kind of geometric interpretation of the Voronoi diagrams. So you can see again the different nodes, so X init, XA, and XB, and there's these circles around that tell us a little bit the kind of radii that we have, and also the Voronoi regions are drawn like that with a black line. And then let's say you would randomly sample a point up here, then what you would do is you would automatically pick X in it, and then because you had this best neighbor expansion, you would again pick XA. Similar if you're selecting something up here, you also would pick X in it, but then because of the rule of your expansion, you would again just expand XB, nothing else. And then if you sample something down here, then you would just select in the tree, for example, XB or XA, and then you're already in the problematic zone because you have no points in between. From the time step 0, you will never be able to explore this space. Okay, so that's quite crazy that they came up with that example. But still interesting because it tells us we have to be super careful when we implement things, how we implement these concrete functions, like do we sample T, how do we explore in order to retain theoretical guarantees. To be fair, even in this example, it is very unlikely to end up with this tree, right? But it is a possibility. And so, yeah, we have to be careful. Any questions regarding completeness and non-completeness of RRT? Yeah. Interesting. So the idea of most completeness definitions is that any problem definition you put in, the property should hold. So also, like if you think about A star, completeness there means you can construct any graph you like, and it should also work. So similar in motion planning, when we say we're probabilistically complete, then we should be able to come up with any crazy example, and it should in principle work even if the probability is low, right? But it shouldn't be 0, and in this concrete case, it's exactly 0. That's the problem. Yeah? No, so the version we implemented was actually this guided Monte Carlo. But if you would now change it to guided Monte Carlo, that count example doesn't work anymore, and your algorithm would be complete. Yeah. Exactly. So for this count example, so there were, I think in the paper they also had the fun table about which RT variants have been probably theoretically analyzed, and there were also some combinations that nobody really has looked at yet. Exactly, yeah. And that's kind of the interesting thing. So if you do everything random, you're usually good, but in practice, your convergence rate is not so great. And that's why people tend to then replace in these randomized algorithms some parts with something that's not random, like in this case. Oh, I have an analytical solution. Let's do that. And then suddenly your theoretical properties might go away. So that's maybe the main takeaway as a warning sign that while you try making some algorithm faster, be careful because you might change the underlying properties. also looked at probabilistic roadmaps. So that has also been shown independently, and this is other papers that's referenced over here. And I use kind of the same notation from the papers. That they also look at the minimum clearance, but here they call it R, not like delta, like we did before. And they also looked at a cost function. For them it was path length because it's a geometric planar. And that's kind of what we want to minimize. And then remember in PRM we had these kind of like two major steps. First we generate vertices that are in free space, and then we try to connect edges, so the kind of neighbors, as long as they're also in free space. And then for the proof, it's also quite geometric. So the idea here is that we now put again our configuration of the solution path, and we put exactly, if our path is L long, we put like 2L over R intermediate points there. And the idea is, and also equidistant, so the idea is that if we now draw our balls around it, so for each pair, consecutive pair on the solution path, the distance between them is smaller than the radius over 2. Right, so graphically we have kind of here two configurations or states, and then the smaller circles are these radii, and because the radius is like that, there's a large overlap between them, and the other point is always also in the other radius. Okay, and then we also have kind of a larger circle or ball that has the radius r itself. So this is this one. And then geometrically, what we can see is that kind of every point that is in this sort of ball and the smaller ball is also contained in the larger ball, just as a triangle inequality. And then the idea is, okay, now I can take any point C that's in the ball around the first configuration or state, and any kind of point that is in the second one. So for example, C and D, in this example, they're on the boundary, but it could also be just inside of these circles. And then if I connect them as a straight line, they're also guaranteed to be collision-free, just because the straight line segment is always guaranteed to be contained in this larger ball, and we said the solution is kind of robustly feasible, which means this sort of larger ball is definitely in free space. Okay, and then once you have this set up, now you can again reason about probabilities. So assume that we have generated these n different points when we sample our vertices for our PRM. And then the question is that do we actually have, and then we put these balls around it, and then the question is, do we have for each of the solution configuration actually a ball or not? And we can compute that also in terms of probability. So if we look at any of these n samples, so sample I, so probability of actually like having this sample as part of this ball qi from the solution is again just the same volume argument. So you just look at the volume of the ball itself versus the volume of the total free space. And I think we can agree that this will be also strictly positive in the cases where n is finite at least. And then we can look at the probability that it's not in that ball, and that's just 1 minus the same sort of probability, right? And then we can look at the probabilities that no sample is in the ball, and then that means we have to repeat the thing n times. All of these things are independent events because we sample independently, which means probabilities just multiply, which is why we get this nice power in here. And then the probability of not finding a solution is bounded by that at least one of the balls is empty, because that would be a kind of a problem that for one of the things of the solution paths, we didn't have like a vertex. And that we can then compute. That would be kind of just looking over the whole solution path and then checking if no ball is there. And that's just kind of sum. And then we can replace it. All of these probabilities inside the sum are the ones we have already. And then this number k was just 2L over R rounded up minus 1 from this minus 1 over here. And so you get this fun property. And then more generically, the form of this probability looks like that, if you kind of try to simplify it a bit. So you have 2L over R, and then an exponential function, and there you have n R power d, and then some alpha constant. And what's really interesting here is that this is actually exponential in n. And n, remember, was the number of vertices we sample, which means the convergence should be really fast. Again, we talk about completeness convergence, not optimality here. But just finding a solution should be really, really fast. And I think that's also what we see empirically. So just finding a solution with PRM or the RRT is very, very fast. Yeah, and so similarly, you can try to figure out what the kind of convergence rate is for RT, and it also turns out to be basically exponential in the number of sample iterations that you take. Okay, then maybe it's always, if you see these sort of equations. Okay, before I start, maybe any questions regarding the convergence? Okay, so then I have some questions. So always a good trick to check if you understand it or not is for yourself is to play with a little bit of numbers or changes. So the first thing we can consider is, let's say we change this R. So R was this robust feasible distance from, let's say, 1 meter, so that it's easy, to half meter, so we half it and reduce it. What would happen with our convergence rate? And by how much? Is it linear or? Exactly. So that's that intuitively also makes sense, right? So if it's, you have a narrow passage, it's less robustly feasible, probability of failure increases. You have a question? Okay. Okay, and then also that same question we had before, let's assume now we have a problem that's not robustly feasible. We had this example at the very beginning, just two obstacles touching each other exactly at one happens then? And I mean with the equation. Yeah. Exactly. So at least it's not defined, I would say. Maybe if it takes a limit of section infinities, that's true. Yeah. And then could you also take this result now, and that result is basically telling us the convergence rate. Can we take it to show probabilistic completeness? And then thickness as long as on the side positive 0. Okay, good. Then we talked about completeness and also kind of the convergence speed of completeness. So let's also look at optimality. It's the same game. Let's assume we recap the algorithm. So optimality classically means that in a finite amount of time, we will always find a solution with the lowest cost if the solution exists. So most notably, we don't have the second statement here about what should happen if no solution exists. Do you have an example of an algorithm that is optimal? Yeah. Different optimality. Yep. So this classic definition is true for A star. Then we also learned bounded suboptimality. It's a while ago. But here's the idea is the same finite amount of time, we always find a solution. But instead of finding the solution with the true lowest cost, we have this user-specified parameter epsilon, and we find a solution that is kind of at most epsilon times the optimal solution cost. Do you remember any example of an algorithm that is bounded suboptimal? No? That's also long ago. So I think we had two. One was weighted A star. That was like a very simple version. And I think we also had focal search or A star epsilon. Okay, and then finally we have this, or semi-finally, but we have asymptotic optimality. Here we reason about probabilities. So in particular, it's asymptotically optimal if the difference between the solution I find and the optimal solution is greater than epsilon for any epsilon, that probability goes to 0. What is an example for asymptotic optimality? Perfect. And we also had this one kind of in passing, I would say, which is asymptotic near optimality, which is now related to this bounded suboptimal. So same definition, but we get this epsilon in here. Do you remember which algorithm had this asymptotic near optimality property? Exactly. technically only the star variant, but which we didn't discuss. Okay, good. So does optimality imply completeness? Yeah. Mhm. Any counter arguments? No? Okay, so in principle I kind of agree. There's just this one corner case, this, at least in our definition. So to be fair, like sometimes these definitions also vary a bit. But in the definition I had on the slide, basically for completeness, I had this condition: if there's no solution, I tell you what should happen. But for optimality, we didn't. And so that makes it a bit more tricky in this case. So for our definitions, I would say no, just because of the slight difference. What about asymptotic optimality? Does this imply probabilistic completeness? I agree. Okay, now we have like looked at asymptotic optimal definitions again, and so we can very briefly also just look at the results in the context of motion planning. So asymptotic optimality has been shown for PRM star and also RRT star. So in the context of PRM star, that's maybe the easiest thing. The way the proof goes here is that we still use these series of balls arguments, but at the same time, like when we look at iterations, we look at how many samples do we use for our probabilistic roadmap. And here we just say that we also change the robustness. So we start with kind of very large robustness and then shrink it. And as a limit, the robustness would be basically 0. And then we try to analyze this probability, which more or less comes from the definition. So in our kind of nth iteration, what is the difference between the solution costs that I actually found and the optimum for this iteration? And remember, each iteration has kind of a different kind of robustness, which means that for larger ends, its cost will be larger, right? Because our robustness is higher. Sorry, for smaller end, the cost will be higher, and then as our n increases, our robustness decreases, which also means the cost will potentially decrease. And then basically the proof shows that this sort of sum is bounded. And then they use this special lemma to say, okay, the sum, this sum here is finite, then the probability that like all of these are true is basically 0. And then in turn we can show that, okay, at least some of them will be 0, which is exactly what we wanted to show. Okay, but I don't really want to go into details just because, I mean, it's maybe not so relevant, but you can read it up in this reference too if you want to know the details. Similarly, for RRT star, it's still the same sequence of balls ideas, but we now have to take care of the ordering. So we have to kind of avoid these funny little jumps that we have here in green. And they have years ago, which is quite interesting. The people went back and said, oh, we found like a mistake in that first proof. And they wrote a whole new paper on redoing it. But at the end, it's almost the same. They just one constant or whatever was slightly different at the end. But the general idea is that you also add as a dimension time, just in order to make sure that the order between the sequence of points is kind of like exactly as the optimal solution. But again, the technical details of it are super complicated. Like you can write 8 pages on it, apparently. Okay, and then we also looked at AOX last time already. I don't want to repeat it, but we kind of made this assumption that the underlying algorithm is complete and that we make this progress in every iteration. You did a very concrete example of that in the last exercise. And then we actually looked at the complete mathematical details in 2 lectures ago, which were like maybe 4 or 5 steps. And the idea was exactly the same. We compute some probabilities, we bound it with some lemma in order to get the show that this probability converges to 0. Okay, and then also kind of in the exercise, you played a little bit with these computing convergence rates and also discussing why this doesn't really tell us anything useful in terms of real convergence rate. And in fact, in practice, the convergence to an optimal result in AOX is very, very poor. It takes a long time. Okay. Any questions before I go there about just asymptotic optimality? Okay, then one question is always, can we quantify how quickly we converge to the optimal result? And at least for PRM we can. I've written down kind of the result of the rate. And again, we have n as the number of vertices, d is the dimension, PRM is geometric, so that would be either 2 or 3. Typically, maybe for manipulators it can be higher. And rho is just some sort of constant. And maybe what's important to notice here is that this is not a really great rate. So when we looked at just finding any solution, any feasible solution, we had this n as an exponent, which means we exponentially fast will find any solution. But here the n is really just kind of like a linear term, and then it even gets reduced for higher dimensions. Right? Like if d is 2, it's almost like a square root or whatever. Right? So it's not so great. Okay. Any question about convergence rates? Then I have kind of one last interesting remark just on the theoretical side. If you remember, I think at the very beginning when we just talked about sampling theory, we also very briefly looked at this thing called Halton sequence, which is a sequence that is kind of like a pseudo-random number generator that creates this very uniform looking results. And so one big question is, if they look visually so nice, what impact does it have on the theory? And there has been at least one work that tried to analyze it. And it turns out that if you do that, it remains asymptotically optimal. So if you use Halton sequence as a random number generator, for example, in RRT star, like one PRM star, that will remain asymptotically optimal. And just empirically, you can basically use, when you think about RRT star, you had these kind of connection radii, so you can use smaller ones, so it makes it faster, and you can even now bound the suboptimality convergence rate, which means you can very concretely say, if I want a solution that is within a factor of 2 of the 2 optimal solution, how many vertices would I need to sample in order to achieve that? And then they also compared it empirically, and well, it's a paper, so they had to show some advancement, and in their work it was better. If you look at OMPL, people still usually use just uniform sampling, even though the Halton sample is also implemented there to play with it. Okay, that brings me to part 2 for today, unless you have any questions. Very good. Then we covered the theory, and now we can look at some more variants of sampling-based planners. We will mostly look at geometric planners, I think, but not exclusively. So the first one I want to bring up is EST, which stands for expansive space trees. It is actually, I think it was originally developed at the time of RRT as like a second version of it. And you can also apply it, for example, in the AO framework, and then it becomes AO EST instead of AO RRT. And it's super similar to RT, so we kind of have sort of the same input, and we also start building up a tree with the start node. And then the main difference is actually in the first step. So in RT, what we do is we sample a random point in our configuration space, and then we use this Voronoi bias to find the closest thing that's in the tree. In EST, instead, we say we have some sort of a probability distribution that's associated with all of the vertices in our tree, and we just randomly pick based on that distribution. Which also means that in EST, you don't have to use a KD tree, right? Because at no point you really have this nearest neighbor switch, because you directly pick from the elements that you already have in the tree which one to expand. The rest is fairly similar, so we then randomly sample a control or like a direction in the geometric case to move away from Q. And then we do our little check and add it if it's collision free. And so really the tricky part here is this probability distribution. Because you can kind of imagine that this is something that changes over time. So ideally, we want to do something that's similar to this Voronoi bias idea, that we try to minimize dispersions. That means that if you want to explore really well, we should always pick kind of an element that doesn't have many neighbors, right? And in RT, that was implicitly achieved with the KD tree lookup. Here we need to do it explicitly by defining our distribution. And unfortunately, the distribution changes the object, new vertices. And so if you look at real implementations, for example, in OMPL, what is done is that you try to compute this dispersion online in a kind of discretized approximation. So you discretize your configuration space, typically in some sort of grid, and then you can count the number of vertices that fall within each grid cell, and then the probability would be inverse proportional. So you would always try to kind of select one where you have very few things, and that would mean you explore pretty well. And so the main challenge is, of course, to define it efficiently. In OMPL, you have these projection operators. So even if you, let's say, you have a high-dimensional dynamic system, you would maybe only take the kind of geometric components where it's fairly easy still to define a grid, and then do the count. Okay, so that's EST. I think in practice it actually looks sometimes better than RRT if you manage to define this function very well. And that is very context dependent. Okay. Then the next algorithm I want to discuss, unless there's a question about EST, is called RRT-Connect. RRT-Connect is an algorithm that many practitioners recommend to use first for geometric motion planning problems, just because it finds solutions very quickly, and these solutions are typically even high quality. And the key idea is to bring bidirectional search to the domain of sampling-based planners and to RTs. So the key insight is that instead of having one tree, we use two trees. One is rooted at the start, one is rooted at the goal. And then at every step, we also try to connect these two trees. So here's a little example. We have our start configuration with some tree, and we have our goal configuration that also already has some tree. And then currently what we do is that we kind of extend the goal tree on the right side. So we kind of sample this point. We found this node over here that is the closest. And now we try to connect. We don't try to go to the points that we sampled, but instead we try to connect to the other tree on the left side. And for that, we find the nearest node of that target one in the left tree, and then we just take these steps. And we can even take multiple steps if we want, or just one step depending on the implementation. And then once the two trees are connected, like in this case, then we have a solution that we can report. And you can imagine that especially in these kind of benchmark instances like narrow passages and so on, it is very beneficial to have a tree that solves from both sides. Okay, and here I have the pseudocode from the original paper, and I kind of put it down because I liked how compact it looks compared to kind of this visual explanation. And so maybe you can take some time and try to figure out what's the purpose of the swap operation in line 7 is. Yeah.
Guess we can extend tree A and extend that. So if we want to be able to choose, we need to export the pointer to just extend, totally extend to the trees in each iteration.
Yeah, perfect. And the alternative would have been to have some sort of counter like this K, and then have like a modulo check and check if the K modulo 2 is zeros and do 3 visualize the tree, right? It would have been much longer. So this is neat and compact. And just to give you visually some examples, there's always like RRT-Connect. Once you, on the left side you see the tree, on the right side you kind of see this final solution for geometric shape that has to move around. And one thing that you may notice is that the tree is very sparse, like even in regions that are not, that are kind of close to the start of the board. And it's very atypical. If you try to visualize the trees that you created during your assignment, you're seeing that the trees tend to get very dense very quickly, especially kind of near the beginning, and very sparse near the end, because once you found something, you stop, right? And this is even true for these sort of very difficult cases like this. If you would draw an a circular RT, it would look crazy, right? Like from the start point would be very dense, and over here would be almost nothing. And also, like in this example, there's some kind of rotation involved, still pretty sparse. Okay. Then we talked about RT star, but not PRM star. And the kind of difference is very close. If you look at PRM stars, the pseudocode is very similar to what we did kind of in the lecture. So we first sample a bunch of vertices, like we did up here, and then we try to create edges. And the main difference for PRM stars is kind of a funny equation over here that uses like a radar for what neighbors mean that depends on the number of samples that we have, right? So the more samples you have, the smaller the radius becomes. And that means that compared to like this classic version that we had with this neighbor, the main difference now is that this is neighbor function kind of depends also on n. And there's some sort of equation that tells us what the radius is. And maybe I'll skip this question and instead move to another PRM version. So this one is LazyPRM, which is quite old, but still it achieves very good results in practice. And the key insight is that in many practical cases, we spend a lot of time during motion planning just collision checking if our vertex or our edges are really like in free space or not. And so the key idea of LazyPRM is that we kind of build a roadmap ignoring the potential conflicts, and we search for shortest path in that roadmap, and then we only check for collisions in the final solution path that we found. And then if it's collision free, we are done. If there is still a collision, then we try to repair our roadmap to address it. Typically means we have to remove things that we now figured out are actually not valid. Okay, and then there's this like special thing that we just briefly discussed. If we couldn't find any paths, then we have to add additional things to the roadmap. Okay, so what do you think would be kind of a good strategy for collision checking if you want to minimize the number of collision checks? Yeah. So in this case, it's this classic PRM thing that you sample a fixed number of vertices, and you already build a roadmap. So there's no real notion of most recently. Okay, so I can tell you what they did, but I mean that's not the only option. So they basically say the start checking just vertices, but also by distance from the start and goals. So first start and goals, then the second ones, the third ones, and so on, going kind of inwards to the middle. Then if that didn't find any collision, then they check the edges, but also this like mixed granularity. So like the traditional way is that you like very uniformly sample your edges in a linear fashion. What they do instead is this hierarchical fashion. So they first start with the midpoint of each edge, also first close to the start and goal, and then if all of the midpoints are fine, then you can split it again in half, kind of similar to a binary search, which is kind of this third and final step. So here's also just some visual examples. So again, in this very first step, we generated a roadmap, but we completely ignored the obstacles. The obstacles aren't great. And then we use a star to find the shortest path in the roadmap. And then we would do collision checking. So first this one and that one, then this one and that one. And then we already find collision, like here, and I guess technically also here. And once we find a collision, we can stop doing collision checking. Right? Which means now we can remove that vertex. If we remove a vertex, also all the edges that go in and out from it get removed. So our roadmap becomes sparser, and we can repeat. So now we plan again from our start to the goal. And again, we check from here to here, and we find there's another collision. We remove it, removes a lot of edges too, and repeat. So now when we check all the vertices in this kind of order, all the vertices are kind of fine, which means the next thing we try to do is checking the edges by going at the midpoints. So we have a midpoint here and a midpoint here, but technically also here and here. And then we already find a collision over here. So we have to remove just an edge and repeat again. And then after some time, we finally find a solution. And then what can happen in this case is, unfortunately, that we like remove tons of stuff, and then at some point our A star will say, oh, there's no solution anymore because the start and goal are not connected. And for that case, they have what they call the node enhancement, where they essentially add additional vertices and also edges to make the roadmap denser again. And they use this like very engineering style thing where they try to figure out likely regions where there are no collisions and add that to the roadmap. Okay, and so LazyPRM is also something that's implemented in OMPL. When I last checked the code, it had just a very basic version. It did not have the like node enhancement, as far as I know. They also implemented LazyPRM star and LazyRT, for which there's no paper to my knowledge, but I mean, you can extrapolate from this idea how it's not so difficult to include it in the other variants of the algorithm. Okay, any question about LazyPRM? Then we have one more algorithm to look at. This one is newer than all the other ones at least. It's called Fast Marching Tree, or FMT for short. And there's also a star version. It is just for geometric motion planning. And it's like the kind of name comes from this fast marching method, which looks at how a wave is propagating in a liquid. So here's some examples down here. So let's say you throw a stone or something in the water, this is black thing, and then you can see if you discretize everything, how the wave would spread through the system. Yeah, I kind of find the name a little bit weird. We can see it once we look at the method itself. But that's what they kind of claim as they came up with the name. Now, algorithmically, it is related to basically RRT. And the idea is that we have many different sets now, and that we also rewire as we go. And maybe it's easiest if we look at it visually. From the pseudocode, the most important part is that we have these three sets: an open set, an unvisited set, and a closed set. And then the rest we can maybe look at as an example. So let's assume we already have a tree over here that's X in it and has some nodes. And you can also see the color of what it is. So that initial start node is in the closed set. We have 3 items in the open set, and then we have some more in the unvisited set. And then we currently maybe have picked this one node Z that is part of the open set, which has, I think, the lowest cost, as we always pick. And we try to find neighbors with some radius that are unvisited. So in this case, it would be these 2 things, right? Because all of the other nodes that are within the circle are basically in the open set or in the closed set. Okay, and then for each of these neighbors, we do the following. Remember, kind of called that. This one is now one of the neighbors, and radius has changed. That one is one of the neighbors. Now we put again a circle around it, and then we now try to find all the possible things that are open, which would be just 2. So that was the one that we started from, and this one is another one. And then we consider both of them and kind of look at the cost. So would it be better to go from here to X, or would it be better to go from Y to X? And for this check, we really just look at the cost. We don't do any kind of validity or collision check yet. And in this case, the cost here for this connection would be better. Then we do the collision check, and we add it. So it's very similar to RRT star and rewiring, with the exception that we don't just rewire, we already pick the correct parent during the expansion step. Yeah, and once we are done, we kind of put that node as a closed set, and we kind of repeat the whole procedure. And so kind of the main difference to RRT stars that here we really need to kind of, at least in this pseudocode, we need to pre-sample all the vertices, because we need to fill these initial sets of vertices. Otherwise, it doesn't work. And then we have these different sets, and they essentially allow us to use this local pattern optimality instead of trying to first make a mistake and then repair it. And so when they kind of came up with this thing, what's new is that they really could also minimize time and space complexity. And I think also in practice it works quite well as long as you do geometric planning. For kinodynamic planning, there's no way to really extend it because you would need to solve this boundary value problem. Okay, any questions about FMT? Good. Then, in the interest of time, I will probably skip this and just let Andreas next week also recap optimization at the beginning. So you should find next week's just a copy of exactly the same slides at the beginning of next week. Okay, so to conclude for today, we looked at different forms of completeness and different forms of optimality, so we kind of recapped all the definitions. We introduced this robust feasibility idea, which then helped us to make some of the proofs for completeness at least a bit more concrete. So especially for completeness, we looked at more of the mathematical details and how we can show RRT, which is the completeness of RT, which we haven't done before. We also considered kind of the convergence rates for both completeness and optimality. We didn't really look into detail on how exactly they are derived, but we at least identified the situation that it's exponential in the number of vertices for completeness, but not so great for optimality, which I hope you have also found during your programming assignments when you looked at example cases. And also, like, maybe the main purpose was to give you an intuition on how these proofs work. And most of them are very similar in style and tools they use, so just kind of very basic probability theory and making sure that the probabilities are non-zero. And then we had quite wide array again of variants of algorithms, namely EST, RRT-Connect, PRM star, LazyPRM, and FMT star. That was quite a lot, but I hope you have also seen that ideas kind of reappear. So once you have understood the basic formulation, it is not so difficult to understand the other sampling-based planners. And the next week, Andreas will talk about optimization-based motion planning for like kind of the first week, and then the week after, I think I will be talking about some more optimization-based motion planning. So we will in total spend 2 weeks on the topic similar to the search-based topics. And if you're interested in learning more, then I mainly recommend looking at these papers that were always in the slide files. Okay, that's all I have. Thank you very much, and let me know if you have any questions.